test is tomorrow. Okay. And the majority of the test for tomorrow is multiple choice. There is some math with the waves, the frequency, the wavelength, and all the energy questions. There are some of the questions that are on here that are kind of worded a little bit differently than what's in the notes. The test will be worded exactly the way that I have it in the notes. However, this is just another way to get used to how things are phrased. But again, it's going to be how I present. All right, so looking at number 1, says a region of high probability of finding an electron. Again, when we talk about what the definition of an orbital is, orbital is a region of space where you're likely to find an electron. So again, just another way to word that. Number 2, the lowest energy level, ground state. So again, what that means is that none of the electrons in that atom are excited. So they're all as we would write our electron configuration. B, the tendency of electrons to enter orbitals from the lowest energy level first. That is the all-ball principle. And again, when we draw out the electron configurations, pretend that we have our nucleus on the left-hand side. We want to get the electrons as close to that nucleus as possible before we fill up higher energy orbitals. 4, the arrangement of electrons around
Number
5. Each orbital has at most 2 electrons. So again, deals with Pauli exclusion, even though the Pauli exclusion principle deals with all 4 quantum numbers, and boiling down to that no more than 2 electrons can have the same spin. So they have to be opposite. Questions on this first 5? All right, looking at 6 through 10, energy needed to move an electron from an energy level to another one. In the notes, I had that at the beginning as a quantum of energy. You won't hear me use that terminology. We don't use that in AP chemistry. I will say what happens when energy is absorbed or what happens when energy is released. So just to make sure we're on the same page there. Number 7, the number of wave cycles passing a point per unit of time. That's your hint right there, per unit of time. So that's frequency. The distance between wave crests, wavelength. 9, the separation of light into different wavelengths. That is your spectrum. And it's like Cooper and Taylor chose wisely, sitting underneath the poster there. Has all the answers up there. But I know you won't look at that. You have that memorized. Number 10, frequency of light emitted by an element. Again, that is our atomic emission spectrum, or that bright line spectrum that I talked about that one day. Not going to talk a whole lot about the bright line spectrums, sadly. Looking at the 11 through 13 here, the third quantum number indicates what property of an electron, but more importantly, let's talk about each one. What does the first one, N, represent? What does N represent? The size or energy level. Good. So the size, so the bigger the energy level gets, the bigger that size gets. Okay. The second one deals with shape. Okay. So you have S orbital, P orbital, D orbital, F orbital. That's as high as we go. And then the third one deals with orientation. So that position is the closest to what orientation is. So, and again, all I want you to know is that for P orbitals, there's 3 possible different orientations. For D orbitals, there's 5. For F orbitals, there's 7. For S, there's only 1. And then the last one, the S, that deals with the spin. So make sure they're oppositely spin. 12. What's the maximum number of F orbitals? But let's talk about each level. What's the maximum number of S orbitals per energy level? 1. Maximum number of P orbitals? 3. Maximum for D? 5. And then F is 7. 13. The shape, not the size, of an electron cloud is determined by the electrons. Yeah. And that's another name, energy sublevel, or sublevel is orbital. So that's not a very good question, in my opinion. Number 14, according to the Abel principle, we want to make sure that we're filling electrons in the lowest energy level first. So electrons enter the lowest energy level first before we occupy the higher energy. So D should have been how many half-filled orbitals are in bromine? So when we look at all the orbitals for bromine are filled up all the way up to, here, let me pop the periodic table up so we can see. So if we look at, where's the periodic table at? Okay. So looking at bromine, okay. So bromine's right here. So the 1s is filled, the 2s is filled, the 2p is full, the 3s is filled, the 3p is full, the 3s is filled, the 3b is full. But when we look at, say, these, okay, you would write out your brackets and then drop 1 electron in each. How many total electrons are we showing for our, what is this, 4p orbital? So there should be 5, so that means that we have that. So how many half-filled? 1. If I were to ask you about, say, arsenic, how many half-filled orbitals do we have for arsenic? Okay, so again, looking at arsenic, and if we fill them all up till we get to 4p, okay, how will we put the electrons in there? Again, arsenic is right here, right? Not AR. So we'll drop 1 in each. So we have 3 half-filled orbitals. That's what that means. Okay. So again, what we're not doing is we're not doubling up. Okay. Make sure everybody gets their own room until we're forced to share. Okay. Or double up. Nobody likes to share, but yeah, that's what we all say. But what's the reality? Amen. All right, where are we at? 16? Okay. Which of the following colors of the visible light has the longest wavelength? So, again, look, make sure you know good old Roy G. Biv. And we talked about this is low energy, or this is high energy. So when we talk about energy in relationship to wavelength, what is the relationship? So as the, say if the wavelength goes up, then what happens to the energy? Yeah, it's inverse. Okay. So bigger wavelengths relate to lower energy. And if I were to say, okay, I've got my frequency, how would we relate that to higher wavelengths? What's the frequency? Is that high or low? Low. Okay. So remember that energy and frequency are the same. Wavelength is opposite of those two. And that table that I gave in the notes actually illustrates that. Okay. Actually, let me show you what I'm talking about there. So again, notes. Say that again. Yes. Yeah. Sorry. So the table. Yeah. Make sure you know that for tomorrow. Okay. So know that radio waves are here, gamma are down here, and everything in between. Okay. So again, that table is lots of good questions in that table. So I might ask, okay. Now, it's easy to answer in front of you, but I might ask, okay, who has higher frequency, infrared or ultraviolet? Okay, so make sure that you can answer that. Without the table in front of you. All right, number 17. Oh, I just answered that. How are frequency and wavelength related? They're inversely related. So A on that one. Number 18, as energy changes of electrons and atoms increase, the frequencies of the line also increase. So that actually was explained, those two from that graphic just a second ago. Number 19, which of the following quantum leaps would be associated with the least amount of energy absorbed? So the key here is least. Okay. So which ones can we automatically cross off from number 19? Because we're, I'm sorry, say that again. A, Is there any others? C? D? Which is it, C or D? I hear C again. Why can we cross off A and D? Those represent what? Yes, Spencer. Releasing energy. So anytime you go from a high to a low, that's releasing energy. So energy is released in the form of what? So if an electron absorbs energy, it jumps up. Yeah, so we're going to have a photon when it returns back down. Okay. So we can cross off, because it says energy is absorbed, we can cross off A and D, because if you absorb energy, you're going to move to a higher energy level. Now, if it says the least amount, we're looking for the least change. We'll make it simple. Okay, so going from 4 to 5, that's a change of 1. Going from 2 to 5 is a change of 3. So the best choice there is B. Okay. Make sure that you can determine how many orbitals there are in a given energy level, how many electrons there are in a given energy level. So, and I know it's probably not too visible for you guys in the back. So N2 tells us how many sublevels or orbitals we have in a given energy level. And then the number of electrons is that equation. So again, no more than, and I think that's coming up soon here, no more than 2 electrons per orbital or per dash. Does that make sense? Okay. And again, there are more than 4 energy levels, but for what we're doing, we won't go beyond that. Okay. And what I mean by that is in terms of s orbitals, p orbitals, d orbitals, and f orbitals. So our periodic table that we have today doesn't have anything that goes beyond f. There are no g orbitals represented here, which is good, because then we need a lot more space on the paper. Okay. The 2 represents, okay, so the N2 represents how many orbitals, and then the 2 represents 2 electrons per orbital. And remember, you do the order of operation. That's why I went ahead and put in parentheses. Okay, even if that's not necessary, anytime you have an exponent, you always do the exponent first. And then 21. Principal quantum number N represents the size or the energy level. And I think somebody else had something different first hour. Anybody have a different answer to that? I can't remember what they said. Daggone. I can't think of it right now. But if you had size or energy level, that's good. 22, the number of orbitals in a given energy level is n squared. Looking at, there's our no more than 2 electrons per orbital. So 23, the maximum of 2, can have no electrons, can have 1 electron, no more than 2. And then 24 again is showing that same equation where we have 2n squared. Now, true, 5th energy level, there are 25 orbitals, but we're not getting into the G's. But I could ask you on a given energy level how many electrons we have or how many orbitals. What do you mean? For doing what? I'm sorry. For like down here or up here? Oh, 26 and 27? It's all the same to me. I can look at the periodic table and just know what to do. It's different for everybody on that. In other words, like looking at the phosphorus, I know the phosphorus is right here in the p orbitals, the 3 p's, so there should only be 3 electrons. Make sure that you are, if you are doing the, probably not a bad idea to separate so you can see that, okay, the p's do have 3, the s has 1, the p's have 3. And then when you get down here, drawing lines in between the different types of orbitals might be helpful in knowing that you have the correct number of dashes. I'm not going to require you to do the verticals. I know I showed it when I represented it the first time in class, just to give separation for you guys so you could see it. But no, it's you can count them and make sure that if it's neutral, that they should have the same number of electrons as protons, unless it's an ion. Is that what you're asking? Looking at 28, explain why the correct electron configuration of oxygen is 1s2, 2s2, 2p4, and not 1s2, 2s2, 2p3, 3s1. That's hard to say. And in that case, this person is like giving everybody their own room in the 2p and the 3s. We have to fill up the orbitals before we can move on to the next energy level or next set of orbitals. Is that what you're going to say, Julian? Okay. So make sure that actually this represents for an excited electron. Okay. This is more of an AP type question. I won't ask that tomorrow. Okay. But if you see an electron configuration like that, that represents an excited electron. Now one of those has moved up, and we took a snapshot and saw that. We're not in the business of taking pictures here. Okay. 29, label the parts of the wave. Make sure you know what a wavelength is. I don't care about amplitude. I will not test you on amplitude tomorrow. I will test you on nodes. Looking at that set right there, how many nodes are there? Okay. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. And technically, I wouldn't do that to you tomorrow. But technically, that could also be a node where the wave has no height. Okay. Did you get that one right, Celeste? If I were to do that, I would make sure that I brought it up a little bit farther, kind of like this, that part right there. Okay. Yeah, Julian.
You also said that the wavelength could be
Crest. Oh, yeah. I'm sorry. Or trough to trough. Yeah. Sorry. Now, tomorrow I would ask, like, how many waves are there? If I gave, like, some measurements down there, I might ask you, okay, from like here, let's say, that equals like 1, from here to here equals 1 picometer. Okay, I might ask you, how long is the wavelength? 1 picometer. I would hope you would be able to answer that. I swear to God, that's a real question. Even on the AP exam, they ask that. Here we go. How long is that wave? Well, some people would say it's a half a picometer because they think from here to here is the wavelength. Okay, so make sure you know what a wave is. All right, number 30. The product, or when you multiply frequency times wavelength, you get the speed of light. If you put 3.0 times 10 to the 8, that's the same thing. Okay. So it's a constant. The formula for the speed of light equation, make sure that you remember that this is wavelength and that this is our frequency. Okay. And C is a constant. Now, we'll give you the same things that I gave you on the quiz. Let's see. See, 31, wavelength and frequency are inversely related. I know we talked about that already. All electromagnetic waves travel in a vacuum at the speed of light. We do not discuss anything other than the speed of light in this class or in AP Chem. The reality is when light hits a medium, it does slow down. Okay, we don't care about that, not for what we're doing. So we're always going to work with that constant. Take a look at the math. You will see that tomorrow. make sure that you're rearranging the variables. So this would be what's given to you. Make sure that you start off with the variables rearranged before you plug in the math. I do also realize that some of you write your units like that. That's okay. And this one, 1/2 seconds. I'm trying to show just one division line so that it's not crazy looking. Keep in mind that wavelength always has a unit of meters, because in the speed of light it's meters per second. Frequency is always 1/2 seconds. And energy is in what unit? Joule. Good. Which I think we have later on. I think so. What's that? Oh no. All right, 35. When sunlight passes through a prism, the different wavelengths separate into a spectrum of colors. In the visible spectrum, the red light has long or high wavelengths and low frequency. So they're bigger. Remember Roy G. Bev. Red is the lower energy side, and violet is the higher energy side. 37. The atoms absorb energy, their electrons move to a higher energy level, or orbital. These electrons lose energy by emitting light when they return to their ground state. So far, so good. The energy absorbed by an electron for it to move from its current energy level to the higher energy level is increased to the energy of the light emitted by the electron as it drops back. So the energy and the photon have equal energy. 39, math problem. 40, math problem. Everybody happy with the math? And then, sadly, the last question. When an electron has its lowest possible energy level, the atom is in its ground state. Didn't I ask that earlier? Also, there's a lot of redundancy in this. But that's how we learn. All right, so for tonight, here's my recommendation. Take a look at the notes. Definitely take a look at the notes. There's lots of good information. Vocab at the beginning. Again, it's not a matching vocab test. I don't do that. But make sure you know what these mean so that you can answer the questions correctly. Again, lots of good information. Roy G. Bev is huge. Make sure you can do the math. The homework, again, might see some more of those questions back up. Make sure you know that table. There's our equation that we've used quite a few times. Other fun stuff. Oh yeah, make sure that you know what the shape of an s orbital is and the p orbitals. I will not ask you about d and f. Okay? Again, know what s looks like, know what p looks like. I will not ask you about d and f. In terms of shape, I will ask you about how many there are, but not in terms of shape. These? Okay. That one? I have no idea. Did I not show you that video? Okay. I know you don't want to see it again. It's open. Hello. Good morning. Who? Valerie?
Yes.
I don't have a Valerie.
Okay. Never mind. Thank you.
You're welcome. I don't have a Valerie in any of my classes. All right. Make sure that you know S through F. Also, the quantum numbers, you'll need to know what the letters represent. Of course, electron configs. Yeah. And don't forget about electron configurations for ions. I do have more practice. I have more electron configuration practice. Answers are right below. I also have more math. The answers right below. Okay. So there is more practice. I will not check these. These are optional if you need them. Okay. But the answers are right there. What's that? No, they are. Hopefully they're in your notes.